Hiya. So in this video, we're going to be talking about change of bases and transition matrices. And this is basically coming from the idea, I think last video, we talked about how we might have more than one basis for a vector space. So there's multiple bases. So how do we go from one basis to another basis? And this is basically where the idea of change of basis and transition matrices are coming from. So let's start off in this. So in this case, we're generally going to be talking about ordered bases. So just as a heads up. So we're going to start off with some arbitrary ordered bases. So here we're going to start off with some bases, and it's going to be ordered bases. And here you'll notice that it's n dimensional, right? Because there's n elements in the bases. So once the basis is fixed, right, we have some basis, we can now represent any vector as column vectors or n by 1 vectors in the following way. So we take some x, right? So here is some vector, right? This is contained in V. Now this, because it's a vector space, right, we can break this down into some linear combination of each of these components. Now here, big note. I guess I'll put this on the side. EI is not necessarily with a 1 in the ith component. Not necessarily true. EI is some arbitrary vector. So remember, so it doesn't have to be the EI we saw in last time. Here it's just a notation, so just a big note. So how do we represent this? Well, we take these and we do the kind of stupid thing. We just say, okay, well, we'll just make this a column vector. x1 all the way up to xn. That's it. Now here, we have to note that this vector lives inside of the vector space with this ordered basis, right? So this vector is dependent on the ordered basis. So like, for example, how is this dependency working? So for example, if I have some other vector, right? Or some other vector space C, and here I have them f1 to fn. So since B is a basis, that means I can write each of the, so like basically we're going to try to go from the original basis of B, we're going to try to go to C. So since B itself is a basis, we can write each of these vectors, f1 to fn, as vectors, as our vectors. And therefore we can write them as linear combinations of the elements of B. So in other words, what we have is each of the fi. So fi, this is going to just be equal. And here we'll write it in a little weird way. We're not going to do the f from before. We'll have this be a1i, so be the first component of e1, plus a2i of e2, all the way up to ani of en. So here, if you kind of remember, this is just going to be a1i, 1, a2i, all the way up to ani. And here, all of the a, I guess, ki are going to live in R. Okay, so this is nice some way. We can do this for all I. So we can do this, do this for all I. And what this gives us is we can take all of these vectors. So there's n of them, right? Because C is a basis as well. We can put them, smush them all together, and that gives us an n by n matrix. So what we end up having is a1, 1, a2, 1, all the way up to an1. So this one is associated to the vector f1. F2 is A1, 2, A1, 2, A2, 2, all the way up to AN2. So here I'm just using the things there. So we do this all the way until we get to Fn. So here we have A1n, all A2n, all the way down to ANn. So here we have an n by n matrix. And since we're going from a basis B to a matrix C, this we're going to call the transition matrix. So this is what is giving us the transition from B to C. So what we'll denote this is as B transition C. So we'll just denote it in that way. And this is going to turn out to be a transition matrix. We'll define it in a second. But first, there's some things we need to know. So this matrix is basically telling us how to represent elements in C from elements in B. But like, this is not always necessarily going to give us something nice. Like, how do we know? So if I give you an arbitrary matrix, right, how do I know I'm going from one basis to another? How do I know I'm not going from one basis to something where the set vectors are linearly dependent on one another? How do I know this? And this comes from the following proposition. Proposition 115, which basically says if I start off with an ordered basis, then, and I look at this matrix, then an ordered basis, then C forms an ordered basis on V, if and only if this matrix has rank n. So B TC has rank n. So if you kind of remember what rank n means, is you take the reduced row epsilon form of this, and you'll get like all ones of the all one vector, right? So just diagonal ones. Everything else is 0. So that's one way to see this. You've probably seen a different way of seeing this as well, and this is when the determinant is non-zero. So the determinant of this matrix has to be non-zero. Or another way is we can take this matrix and invert it. So all of these are equivalent ways of saying the same thing. So that's it. So this is basically giving us this idea. So there's this sketch of the proof if you want to see it. As mentioned, we're probably not going to go too much into them, but there is. In essence, this is basically coming as a consequence of the rank nullity theorem from linear algebra. So this is very dependent on rank nullity, and how these are kind of equal to one another. And basically, if you have something where if your rank is less than n, you're going to have some row that's linearly dependent on something else, and so you're going to end up having problems. And this is basically what this is talking about. So you're going to get a linear dependence. So one thing to kind of recall, this determinant condition, because we'll use this later, this determinant condition, this will restate here, determinant n is non-zero, and we'll recall that this is, we can either call it non-degenerate or non-singular. It's kind of one way to kind of see this. And now we can finally define what the transition matrix is. So we have a n by n non-singular matrix. So the determinant is non-zero. In other words, we go from one basis to another basis. Then BTC describes the ordered basis C in terms of the ordered basis B. So it's a transition from the ordered basis B to the ordered matrix C. And we'll kind of stop here. Next time we'll go into, in the next video, we'll do a quick example. So the next video will be shorter. And then the next time we'll see inner products. So we'll stop here before looking at a more thorough example of a transition matrix. So I'll see you then.